Hello. Welcome to the Tom Builder channel. My name is Julia, and in this tutorial, I will show you how to build an advanced spindle speed measurement system using a Kubler Sendix encoder, and Arduino ATmega2560 microcontroller and a Nextion display. We'll integrate RPM, motor and inverter temperature measurement, data visualization on graphs, as well as startup logic and cost-effective data updating. The heart of the setup is the Kubler Sendix 5000 incremental encoder, which generates up to 3600 pulses per revolution. This allows for extremely precise speed measurements. Of course, any other type of encoder can be used to measure spindle speed. The encoder is powered by 12V voltage, so its signals A, B, and the zero pulse Z, our use, are fed into the Arduino through simple voltage converters built with NPN transistors, type BC547. Arduino is responsible for collecting pulses, calculating rotational speed, and transmitting data to the Nextion display. Communication is carried out via a serial interface. We also add two temperature sensors, Dallas DS18B20, to the system. One monitors the engine, and the other monitors the inverter. Their data will also be displayed on the screen. With this configuration, we have a complete set: precise measurement, advanced visualization, and extended drivetrain diagnostics. At the center of our Lathe's entire system is Nextion's 7-inch HMI display. It serves as the main user interface on our Lathe. The screen shows all the key parameters of the machine's operation: the current slide position in the X and Z axes, motion modes, feed lengths, set points, and current readings. It's an integrated control and diagnostic panel that allows you not only to monitor the machine's status, but also to directly control its operation. The display also shows all limit states, zero positions, active operating modes, as well as function keys, for example, for resetting axes, locks, or switching to manual positioning. Importantly, we can switch to an advanced view of the spindle speed at any time. Just click on the spindle RPM box. The system will automatically switch the screen to the section with the RPM graph. Okay, let's get started. In this section, we will deal with reading signals from the Z channel of the encoder using the onPinChange function, a logic state change interrupt. With this solution, we do not need to use dedicated hardware interrupt pins. The Arduino Mega allows us to monitor changes on multiple digital pins and trigger a response whenever there is a rising or falling edge on the input. From this data, we will calculate the time between successive pulses, which will later allow us to calculate the exact RPM. The visible code includes definition of pin 13, Z output of encoder, interrupt handling, calculation of time in milliseconds between consecutive pulses, calculation of spindle RPM, memorization of next sample in function, shiftAndAdd, register contains last 5 samples, calculation of median in function, getMedian, allows elimination of RPM reading errors. Calculating RPM requires storing the last 5 samples in memory and calculating the median every 1 second. This allows for a smooth and natural speed reading. Storing the data in memory will also be used later for filling the chart with RPM history and motor and inverter temperatures. The values are simultaneously buffered and stored in the background so as not to block the main program loop. The initial values of all components, RPM counter, temperatures, statuses, graphs, should be defined in the Nextion editor. This ensures a clean and stable start of the system. The Nextion display allows us to perform logical and mathematical operations. For example, we can calculate the percentage of turnover. You can also dynamically change colors, hide or show components based on input, without involving Arduino. Each control placed on the display using the Nextion editor application has a unique ID within the page and its own attributes. The system displays the data in 2 types of graphs. Main chart, RPM plus temperature, covers the last 7 minutes, where RPM is the left axis and engine and inverter temperature is the right axis. And the detail chart, RPM details, shows the last 3 minutes with high precision. The temperature measured from the sensors is presented on the main chart, shared timeline, and in numerical form I-Celsius. RPM is displayed not only as an absolute value, but also as a percentage of maximum RPM from 0 to 100%. This makes it easier for the operator to assess the load on the drivetrain. These calculations can be performed directly on Nextion, which relieves the burden on the Arduino. After the spindle is started, the system runs in intensive mode for the first 8 seconds. RPMs are updated continuously, with data sent to Nextion without delay, allowing precise tracking of acceleration. After this time, the system enters lean mode. Data update every 1 second. New data are sent only when a change in value is detected. The code visible on the left is responsible for reading RPM every 250 milliseconds, calculating the average RPM every 1 second, presenting data if the chart RPM page, ID 12, is active, and writing RPM samples and temperature to memory during spindle operation. It's worth remembering to choose the type of variables appropriately because the Arduino needs to save 1260 samples, 3 times 420 samples because 7 minutes is 60 seconds for RPM, motor temperature, and inverter. The waveform component from Nextion takes the maximum value as 255, so assuming our maximum speed to 1000 RPM, we need to divide it by 5. The code shown on the right is an automatic adjustment of the RPM details chart to the current speed plus or minus 50 RPM. The RPM details chart shows the actual speed but on a finer scale for the last 3 minutes. The scale of the chart automatically adjusts to the current speed. For this chart, the waveform component has a DIS 100 attribute, so each one chart value corresponds to 1 pixel. For the overall graph, the value DIS 200, so be sure to adjust the height and width of the graph to match the scales and auxiliary lines spaced. When the spindle is started, data is collected automatically and stored in memory. Each click on the RPM value on the main screen calls up the following function. At first, the system displays the chart RPM page, beeps, and clears and hides both charts. This is to visualize the data loading process. When finished, the progress bar is hidden and the charts are uncovered again. Data loading is done in a single loop, where all the data, along with chart RPM details, is loaded up to position 180, and then only the data for the main chart is loaded. The progress bar is filled every 40-50 positions for proper visualization. Thank you for your attention. We have developed a complete, functional system for measuring and visualizing spindle speed using Kubler Encoder, Arduino Mega microcontroller, and Nextion display. Thanks to advanced logic, the system responds dynamically during startup and later works economically and stably, offering clear real-time data presentation. We have implemented Z-channel pulse reading using onPinChange, Z-pulse detection for synchronization, RPM calculation from time between pulses, median filtering and data stabilization, graphs with RPM and temperature history, dynamic view switching on the Nextion touchscreen, and a clear, user-friendly operator interface with diagnostic and control functions. It's a powerful tool that can be successfully adapted to other machines, not just lathes. If you want to keep up to date with more automation, CNC, and microcontroller projects, subscribe to the Tom Builder channel. Visible Arduino codes are working and proven functions that work daily in our machines. They are available to any subscriber to our channel. I also ask for any comments, feedback, and ideas. I am also curious to see how you perceive me as an AI avatar. Thank you for your time and see you in the next episode.